Forest plots are the center point of meta-analysis. They are the star of the show. However, many people find them difficult to understand, which is okay. It has a lot of elements and it's the product of very sophisticated statistical software. But if this is your case, not to worry at all. In this video, I'm going to explain every single element of this graph for you, and you will leave this video with full comprehension of how it works. My name is João Evangelista. I'm a medical student from Brazil. I have a couple of meta-analysis under my belt, and this is the Meta-Analysis Academy, where we teach thousands of students from hundreds of countries the science of making systematic reviews in meta-analysis. Let's use an example to understand forest plots. And before we can understand forest plots, we need to understand what is a meta-analysis to begin with. Suppose we get several studies comparing drug A to drug B or drug A against placebo. We gather all the data from all the studies available and put them together using math. If you read one study, you might get one conclusion. If you read another study, you might get to another conclusion. Why? Well, because populations are different. Timing is different. And there's also the obvious random chance. But by combining several studies together, meta-analysis creates a very big picture conclusion, a bird's eye view of that specific topic. In this study in particular, Randerson and his team were looking at SGLT2 inhibitors against placebo for patients with heart failure. They wanted to know if those drugs were efficacious in reducing all-cause mortality for those patients, specifically for the patients with heart failure. They found 30 studies about just that. Okay, so this is the graph for all-cause mortality for the studies in that meta-analysis. So out of the 30 studies, those here, 1, 2, 3, 4, 5, 6, 7, 8, 9, those 9 studies are the ones that showed all-cause mortality. So this is a graph specifically for all-cause mortality. These here are the individual studies. The studies Canvas 2017, Credence 2019, DAPA-HF 2019, etc. They're all studies that compared SGLT2 inhibitors against placebo. And you can see that here. There are the patients that were on SGLT2 inhibitors and the patients on placebo, okay? Okay, so down here at the bottom, we see the pooled results of the meta-analysis. The results, like everything together, the math is summed up right here, and also in the bottom of the graph, okay? I'll explain this shortly. This specific column right here, hazard ratio, it shows the results from each individual study. So we have a hazard ratio of 0.7 for Canvas 2017. We have a hazard ratio of 0.93 for Credence 2019. For DAPA, we have 0.83. For Declare, we have 0.87, and that's so on, so forth. Okay? And just as a reminder, a hazard ratio of less than 1, which is most of them, except this vertex right here, which has a 1.01, most of them have a hazard ratio of less than 1. What does that mean? That means that the treatment right here, which is the SGLT2 inhibitors, they decrease the risk of a certain event which is being evaluated. What's the event being evaluated? All-cause mortality. Meaning that if we have a consistently lower than 1 hazard ratio for all-cause mortality for SGLT2 inhibitors in comparison to placebo, it means that SGLT2 inhibitors decrease all-cause mortality. You understand? Also, on this column right here, you see the weight of the study. And the weight is reflective of what statistical power each study has. So here we have the Canvas 2017 trial. It has 7.8% of the total power of this specific forest plot. Meaning that out of the total results, out of the specific part right here, which is the actual result of the meta-analysis, it is responsible for 7%. And this is determined by the statistical power of that, Canvas 2017 itself. You see here, for instance, that DAPA-HF 2019 is a study with many more patients. It has more than, it's almost 3 times as more patients, and it has more than 3 times as much statistical significance and weight, because DAPA has 32%, and Canvas has 7.8%. This makes the study even more accurate. We're giving more power to the overall result to the studies that carry more patients. And, because they carry more patients, overall they carry more data. See those red squares? They represent the point estimations of each individual study. For example, you see that the lowest hazard ratio possible was the one from Canvas 2017. It's not a coincidence that it's the red point, which is more, farther from the null effect line, which is this line right here, which is 1. Meaning that if the hazard ratio was exactly 1, it would make no difference. But, if it's less than 1, it's less all-cause mortality. And, the farther away from 1 it means that, the more safe the patient is, like the less all-cause mortality overall. And the lines are the confidence intervals. These lines right here, they are the confidence intervals of these studies. If a study is very, very good and it has a lot of statistical power, the confidence interval is lower. If the study is not particularly powerful inside of that analysis, the confidence interval will be longer. Why is that? Well, because the confidence interval is basically saying that, well, our estimation is right here, but it could be right here, or it could be right here, or it could be right here. The actual results could be anywhere in that confidence interval. That's why it's called a confidence interval. Like, we're confident that inside this, interval of numbers, the actual results are. It could be at the center, which is the usual, but it could be right here, it could be right here. You understand? Now, the diamond right here, this is interesting. This is the overall result of the meta-analysis. I'm actually going to zoom in so you can see this. So when you come right here, we know that the overall result of the meta-analysis is 0.86, okay? 0.86. What it means is that, out of all the studies together with those weights, they carry 0.86. 0.86. So this means that right here is 0.86. It's 0.14 away from here, and it's 0.86 away from 0 on the other side of the screen. Is that, understood? Okay, so what that means is basically that the hazard ratio for the overall is 0.86, but the confidence interval of the meta-analysis is represented by the width of the diamond. Meaning that this right here is 0.94 and this right here is 0.79, which are the values of the confidence interval of the meta-analysis. Now, if the diamond tip was precisely in the null effect line, that will mean that there is no real difference for all-cause mortality for SGLT2 inhibitors. But because it's here, it means that there is a difference, and that difference is estimated to be 14%, which is 100% minus 86%, which is the overall result. So it's 14%. That's the estimation. But it could be as low as 6%, because the difference between this point and this point would be 0.06. But it could be as high as almost 21%, because the difference between here and here would be like 0.21, but probably it's right here in the middle, 14%. Regardless, there is a difference and there is a benefit. That's a fact. Zooming out so that I can show the rest of the stuff to you guys. Over here at the bottom, we have the p-value of the meta-analysis. Now, a statistically significant p-value should be less than 0.05. This here is of 0.0007, which is much lower than 0.05. The meaning of this is that this particular meta-analysis is statistically significant. Also, right here, we have the measurement of heterogeneity. This is a measure of how much each individual study differs from the others. So based on these calculations, we can see that there is no heterogeneity in those studies. So based on these calculations, we can estimate that the difference between those studies, the heterogeneity, is 0 or close to it. It shows 0% right here for that specific outcome, which again, it's all-cause mortality. All right, guys, that's it. That's the anatomy of a forest plot. I hope you now understand it completely. And if you have any other questions, please leave them in the comments below. We're going to try to answer them as soon as possible. And if you want to understand how to perform meta-analysis by yourself, click the first link in the description. All right, that's it from me, guys. Bye-bye.